Okay, so in lecture 12, we are going to make a jump between Fourier series and Fourier transform. So what we are going to do is take a look at what happens to a Fourier series as you go from a periodic signal to an aperiodic signal. So that's kind of where we are going. Fourier series to Fourier transform. So I made a MATLAB simulation showing the convergence from Fourier series to Fourier transform, and I posted that. It's a 35-second video. I posted that to YouTube. Uh, Let us see if I can uh, pull that up. Maybe we'll do that later, a little bit later. So wait for the MATLAB simulation just now. For now, if you guys can quickly go to the video lectures tab on Piazza and open that YouTube link for lecture 12 MATLAB demonstration in a new tab, have that handy. It'll be helpful. But first, let's talk about signal classification versus the Fourier series or Fourier transform. The signal type, when it was periodic, we applied the Fourier series to that particular periodic signal to find the AK, the Fourier series coefficients, whether it be exponential Fourier series coefficients or trigonometric Fourier series coefficients. We found Fourier series of the periodic signal x of t. Now, if the signal x of t is a general signal and aperiodic signal, then we need to find its Fourier transform to know the frequency domain information of the time domain signal x of t. So now you will start hearing me use the terms time domain and frequency domain. And when I talk about time domain, I'm talking about how a signal behaves with respect to time. So what is its amplitude at 1 second, at 10 seconds, at 50 seconds, tomorrow, right, with respect to time. And when I talk about frequency domain, I'm talking about how fast is it changing? What is the maximum frequency in this signal? Does it have a higher amplitude at lower frequencies? Does it have a higher amplitude at higher frequencies? What is the frequency domain information, right? So it gives you an idea about how fast or slow the time domain signal is changing. So some students are mentioning that my audio is cutting out. Do you guys see this too, or what is going on? Okay, so some people are saying I'm good, sounds okay, not happening to me. All right, so I'm going to assume that this is okay. This is going okay. All right, so that's the first thing that I want to note going forward. We are going to be talking about a signal in time domain and frequency domain. Time domain, we are observing the characteristics of a signal with respect to time. So the x-axis is time, similar to what you see over here. The x-axis is time, but because this was a periodic signal, we found its Fourier series coefficients. But when we talk about a general signal, which can be aperiodic or periodic, doesn't matter, right? General signal, it can be aperiodic, it could be periodic. We are going to find its Fourier transform. So that's another thing that I want to point out. There can be a Fourier transform of periodic signals as well. But when you talk about Fourier transform, we are looking at the frequency domain information of the signal, and our x-axis will be omega, the radian frequency, or it might be f, either radian frequency or just the frequency. So in time domain, your x-axis is time. Now, let's try to take a look at the derivation going from Fourier series to Fourier transform. Suppose you have a pulse train over here indicated as x of t. It is clearly a periodic signal with a time period cap t. Its Fourier series coefficients are defined as a sub k. And we know from earlier that a sub k can be written as 2t1 divided by t sinc k omega naught t1, where t1 is the time, well, 2t1 is the time for which the signal is on, and cap t is the time period. Because we know sinc x is sine x over x, I can rewrite 2t1 divided by t sinc k omega naught t1 as 2 times sine k omega naught t1 divided by k omega naught t. So I'm simply using the definition of sinc to go from here to here. And now if I bring my t to the left hand side, I have ak times t equals 2 sine k omega naught t1 divided by k omega naught. Now notice this signal. Notice this 2 times sine of k omega naught t1 divided by k omega naught. What are k omega naught? Well, k omega naught, when k is changing, you're scanning over multiple harmonics, 1 omega naught, 2 omega naught, 3 omega naught, and so on, for the fundamental, second harmonic, third harmonic, and so on. So k omega naught is essentially like sampling the function 2 sine omega t1 divided by omega. So ak times t, and that's what we are going next. Ak times t is essentially like sampling or evaluating the continuous function 2 sine omega t1 divided by t at integer or intervals of omega naught. So integer multiples of omega naught. So that integer intervals of omega naught come in at 1 omega naught, 2 omega naught, 3 omega naught, 4 omega naught, 5 omega naught, and so on. And also you have on the other side negative 1 omega naught, negative 2 omega naught, negative 3, negative 4, negative 5. Those are all intervals of length omega naught. Notice over here our x-axis is k omega naught. So as you scan over k from plus and minus 1 or plus and minus 2, plus and minus 3, and so on, you are essentially evaluating at plus and minus 1 omega naught, plus and minus 2 omega naught, and so on. Your y-axis is t times ak. And we just now derived earlier that it is essentially the envelope of that signal for t times ak is 2 sine omega t1 divided by omega. So, but now if I evaluate this, when omega is k omega naught, I essentially get those points, those black samples of the sinc function. Let's see, what is that? T1 divided by T is half the duty cycle. Yes, because duty cycle is the ratio of on time to the complete time period. So T1 indicates half of the on time. All right, let's move forward here. So we went from, so you guys remember earlier we were talking about K versus AK, right? Those Fourier series coefficients we are sketching as AK versus K. Now we are putting in omega naught and over here T. Our shape is the same, but notice what happened. Because we multiplied ak by t, the amplitude of each of those samples got multiplied by t. So a1 and a minus 1 got multiplied by t, a2 similarly got multiplied by 3. All the Fourier series coefficients got multiplied by t, where t is the time period of the pulse train. And our x-axis was k going from 1, 2, 3 and so on. Now we are doing the same thing but k omega naught. So the distance between these two is going to be omega naught, intervals of length omega naught. So what can you say? You can say that x of t consists of sinusoids with frequency 0. Frequency 0, that what does that mean? That means the DC value, and omega naught, that is that 2 omega naught, 3 omega naught and so on. In this case, because we don't have any values for the even harmonics, the contribution from 2 omega naught, 4 omega naught, 6 omega naught is essentially 0. Now let us try to do this. With this information, so far we have done nothing new. All we did was recap the Fourier series of pulse train, and we essentially just multiplied our y-axis with t and our x-axis going from k to k omega naught. That's it. That's all we did in terms of a change. Now is the bridge from Fourier series to Fourier transform. Now let us try to do this. Now let's see what happens when we try to change the time period of this pulse train to infinity. As you do this, as you change t to infinity, because omega naught is simply 2 pi divided by t, omega naught will tend towards 0 as you take the limit of t tending to infinity. What does that mean? That means if I go back over here, if I sketch, if that is t over 2 and I'm evaluating t tending to infinity, what am I doing? I'm essentially stretching this signal out, right? I'm pulling this signal outward. So what is going to happen? Well, instead of changing here, my changes are going to become less frequent, right? The change will be here, right? Instead of here, it will be here. And further out in time. So things will become slower. If things become slower, what does that mean in terms of frequency? Well, if things become slower, that means more things at low frequency. Okay, so what is less frequency? Well, closer, that means closer with each other. The omega naught term is going to 0. So what is going to happen over here? The distance between these, the intervals here, are going to get, consequently they are going to get move towards each other. So as that means that as you stretch out the continuous time periodic signal, you are squeezing in the Fourier series coefficients. Not the coefficients, but you are squeezing in that k omega naught axis. You are essentially squeezing in that axis. Let's take a look at this. So over here we have spread out that t. We have increased t. When we increased t, the envelope remained the same. 2 sine omega t1 divided by omega. The envelope remained the same. However, because the t increased, as t went up, omega naught went down. So the interval over here went down. So now you have more points being represented. And as you make t going to infinity, you will have all frequencies that will get represented. In other words, if you wanted to take a look at the Fourier transform of simply one rectangle, it would be a continuous sinc function. this is essentially captured in that YouTube video. So let me try to pull that up over here. Let's see if this works. I have this guy and then video lectures. I don't know if this is going to work or not, but I'm going to try. Lecture. So in video lectures, it is the first one right at the top. So if I click that, it takes me to this, and I do that, and I do that. Omega naught is pi over 2. Omega naught is pi over 4. Things are getting closer. In time, they are getting spread out more. In frequency, they are getting narrower and narrower, closer and closer. Case 4, omega naught is pi over 16. Case 5, omega naught is pi over 32. And only when you have one pulse remaining, it is looking more and more as the, come on, no. So let's do this again. Time period was 4. Things were spread out. Time period was 8. Things got closer to each other. Time period was 16. Things got even more closer to. Note what is the x-axis on the Fourier series coefficients. X-axis is k omega naught. Y-axis is t times ak. Things are getting closer and closer to each other as I'm increasing the time period. And in the limiting case, where I go to, all the way, t tends to infinity. I went from t equals 4 all the way up to t equals 64 in that particular example. If you go all the way to infinity, that will mean that omega naught will tend towards 0, which means all the frequencies will be represented. So instead of looking at a sampled version of the sinc, you will actually look at the entire continuous sinc in the frequency domain. So the envelope 2 sine omega t1 divided by omega. Now omega is the frequency variable, the independent variable. So in the time domain it was t, in the frequency domain it is going to be omega. That is the one that characterizes the non-periodic signal, the general rectangular function, which is aperiodic in this case. Jacob says, so if this example represents moving towards a Fourier series representation of signal, what should we make of the negative portions of the curve? Let me see. Negative portions of which curve? So it's the same signal, right? So here, there are two things happening here, right? And one is the consequence of the other. If you stretch out your time domain waveform, right? Just imagine you pulling it out, right? If you pull it out, what is going to happen? If you are increasing t, you're not changing t1, you are just increasing t. If you increase t, you are essentially saying that the next pulse will come in at a later time, right? Farther and farther out. You are increasing the time period to infinity. So as you change that, you are essentially squeezing in, consequently, you are squeezing in all the frequencies. So the lower frequencies will now be represented. How can you have negative frequency? Oh yeah. So you can have, so negative frequency is a mathematical entity. It is not a real entity. So but you can have negative frequencies in a mathematical sense, not a practical sense, because they will have contributions in the frequency domain. We don't need to worry about the negative frequencies for now, but as you go forward, you will see that they will play a crucial role when we talk about how we use the frequencies for maybe communication between two points. So they bring in mathematical sense. All right. So let's take a look at what is the Fourier transform. If I wanted to find the Fourier transform of any signal, what would I need to do? Knowing that I'm essentially evaluating this as time period tending to infinity or omega naught tending to 0. So let us start this convergence from Fourier series to Fourier transform by looking at the general Fourier series. What do you have? AK equals 1 over t integration from negative t over 2 to t over 2 x of t e to the negative jk omega naught t dt. All right, we know that. We know the general formula to find the exponential Fourier series coefficients, AK. We have looked at it from many different angles. Now, if you bring this t out to the left hand side, you have AK times t, that's what we are interested in, is going to equal negative t over 2 to t over 2 x of t e to the negative j omega naught t dt. Everything else remains the same. Now, as you evaluate t tends to infinity, AK times t, the product of the time period and the Fourier series coefficients, can be considered as sampling negative infinity to infinity. T is tending to infinity. So negative infinity to infinity, x of t, notice the change, k omega naught becoming omega naught, just omega. So k omega naught, earlier it was being sampled, right? 1 omega naught, 2 omega naught, 3 omega naught. Now it has become a continuous variable because of that convergence. And we are AK at the intervals of length omega naught. So the definition of Fourier transform is cap x of j omega. You are using cap x. Sometimes textbooks use bold capital X. I simply put a bar over the top and the bottom to indicate that it is a capital letter. So, and there is no confusion with the small letter of j omega or just omega, or sometimes you will see this frequency, right? They are all, different notations. A function in frequency domain. It could be f, it could be omega, or it could be j omega. That is defined as integration from negative infinity to infinity. X of t, that is the time domain signal for which we are trying to evaluate the Fourier transform. And you multiply that with e to the negative j omega t dt. So you are essentially integrating out the variable t and you will be left with omega. That's what you have over here, x of j omega. So this is how the Fourier transform of a continuous signal is defined. That's the definition of the Fourier transform. And it comes from, as we saw, Fourier series. There is also an inverse Fourier transform. Why is that? Well, if you have two domains, time and frequency, you are trying to use Fourier transform. So if you have time and frequency, let's see this. You have time here, you have frequency here. These are two worlds or two domains. To go from time to frequency, you use the Fourier transform. To come back from frequency to time, you use the inverse Fourier transform. Sometimes you might be interested in finding out what is the frequency content of a signal. Some other times you might know the frequency content of the signal and you might want to analyze how does it behave with respect to time. So you use inverse Fourier transform to come back. And even this has a definition. So, and it also comes from the same Fourier series. So if x of t is t periodic, we are starting from a periodic signal with time period t. I can represent x of t as a summation of an orthogonal exponential set of functions, each scaled by ak. We know this from the orthogonal set of functions discussion earlier. Note over here you have e to the plus jk omega naught t. Usually there is a confusion between the e to the plus j or minus j. So when you are evaluating the Fourier transform, you will get x of t e to the negative j omega t. But when you're finding out the inverse Fourier transform, you get a plus there. So that be careful about that change. So if you are representing x of t by that, and we saw that ak of t was the sampled version of x of j omega, right? That's what we saw here. Ak of t is the sampled version of x of j omega. In other words, if I had omega as k omega naught, these two are equal, which also means if I bring the t out to the right hand side, ak equals 1 over t x of jk omega naught. And if I substitute this ak over here, I can write x of t as a summation k equals negative infinity to infinity followed by ak, which now is 1 over t cap x of jk omega naught. E to the plus jk omega naught remains as is. 1 over t can be written as omega naught divided by 2 pi. 1 over t can be written as omega naught divided by 1 over 2 pi. And now if you observe this function, x of jk omega naught, e to the jk omega naught times omega naught, that is essentially and a summation. What does that mean? If you consider omega naught as some d omega on the x-axis and two functions over here of omega naught getting multiplied, what do you have here? And a summation. So you're essentially, that is a numerical approximation of an integration, right? Or the Riemann sum. The continuous function can be broken up into smaller rectangles. The rectangles will have a base, they will have a height. The height will be based on the product of these two. The base is d omega, or in this case omega naught, and you sum up all those areas, it will be like an integration. Which means as you evaluate omega naught going to 0, which is what we are doing when we go from Fourier series to Fourier transform, this summation or Riemann sum will become an integration. 1 over 2 pi remains as is. The summation is going to become an integration here, negative infinity to infinity, cap x of j omega now, e to the plus j omega t d omega. So let me color code this. Let me use this guy, maybe blue here and pink here. So this becomes pink and omega, that becomes blue, that becomes yellow. What are the other colors I have? Say green. What else? Orange. I've essentially mapped each operation. I have color coded them, how to go from that Riemann sum to the inverse Fourier transform. So that's how you go from, let me write that over here, from frequency domain. What does frequency domain mean? That means that I have the information of x of omega or x of j omega or x of f. I know that. And I need this. I need the function in time domain. So I use the inverse from frequency domain to time domain. So when you're evaluating Fourier transform, you are going from time to frequency domain. When you are evaluating inverse Fourier transform, you are going from frequency domain to time domain. Now, depending on the application, you might need to go one way or the other. Note, the time and frequency domains will always be in the form of pairs. So you will call them Fourier transform pairs. In other words, you can write this as x of t double-sided arrow Fourier transform x of omega. And that double-sided arrow indicates that it is going to be a pair. All right, so those are your two definitions. One is for the Fourier transform here. Let me clean this up a little bit. That's your Fourier transform. And the other one is the inverse Fourier transform on the next one. Over here, we are essentially summarizing what we just talked about. Definition of Fourier transform and its inverse. The Fourier transform of a signal is defined as x of omega. Integration is you are integrating out the time variable, and hence you will be left with omega variable, the frequency variable. Some textbooks also write it in this form. They write it as x of f in the form of f. So just note that we are going to follow omega. Otherwise, you have to deal with an extra 2 pi, which is fine. But for our class, we will stick with the use of x of omega. Also written as x of omega is the Fourier transform of x of t. And going backwards, apart from the sign change, notice there are two changes here. The sign is different here, and there is also an additional 1 over 2 pi that is missing in the Fourier transform. Also written as inverse Fourier transform, F inverse. X of t, time domain, x of omega, frequency domain. Other notations, x of j omega, x of f. Fourier transform will take you from time to frequency. Inverse Fourier transform will bring you back. And they always appear in the form of Fourier transform pairs. All right, so this is good. Let's move on here, because we need to focus on some motivation. What could the Fourier transform of a signal be useful for? And because we are integrating from negative infinity to infinity, sometimes that integration might exist, or sometimes you might not have a Fourier transform that exists because you are integrating between negative infinity to infinity. So it could go. It is possible that the Fourier transform of a signal may not exist. So we'll try to take a look at some conditions that will allow us to check whether it exists or not. Do all Fourier transform pairs require integration? I'm sure you guys will appreciate doing less integration. And that's the key. Even though all transform pairs can be found by direct integration, which means that using the definition of Fourier transform or inverse Fourier transform, you can find all the transform pairs. However, in most cases, that integration will be messy, which means that it'll either take you too much time to do it, or it will be something that you cannot do it by hand. And so most times it can be avoided. How can you avoid that integration? You can avoid that integration by expressing the unknown complex signals in terms of simpler signals. And then operations whose transforms are known. So for example, a quick example is this. Suppose you wanted to find the Fourier transform of a triangle and you knew the Fourier transform of a rectangle. Then instead of applying the direct integration on a triangle, you can also do this without much integration by using the known Fourier transform of a rectangle and the time derivative property, which we will see later on for Fourier transform. So by using properties of Fourier transform and by expressing complex signals in terms of simpler signals, you can avoid that messy integration. In fact, that is what we will all recommend, right? That's what I recommend you to do. Try to break down complex signals into simpler signals to leverage and use the properties of Fourier transforms. That will save you a lot of headache and time. Next question. Will the integrals always converge? Will the Fourier series, will the Fourier transform exist all the time? No, they will not exist all the time. But they are guaranteed to converge. So it's a sufficient conditions here. Sufficient conditions. This guy is a weak sufficient condition. This guy is a strong sufficient condition. The weak sufficient condition is the signal is square integrable, which means that if you do a magnitude squared of the signal x of t and you integrate it for all time, and that is a finite value, that means it is square integrable, which is a weak but sufficient condition to say that the Fourier transform of x of t will exist. A strong sufficient condition will need the absolute integrability of a signal. So take the absolute value of the signal x, integrate it from negative infinity to infinity, and if that is finite, then that is a strong sufficient condition to let us know that the Fourier transform of x of t exists. And there are many other continuity conditions that are described in the textbook, but we will follow the condition 1 and 2 to quickly evaluate whether the Fourier transform of the signal exists or not. So before you jump into finding the Fourier transform of the signal, it is useful to check number 2, right? Find the absolute value of the signal. What does that mean? That means that flip all the negative sides to the positive sides. Similar to what a full wave rectifier does for you, right? Flipping all the negatives to the positive side. All right. So once you do that, you try to integrate over all time, and if that is finite, that is a strong sufficient condition to let you know that the Fourier transform of the signal will exist. So this can be done by inspection very quickly before you actually jump and try to find out the Fourier transform. Now here is the motivation bit. Here is an important slide. What information does x of omega, the Fourier transform of x of t, provide? The first thing that it provides is the frequencies present in the time domain signal. What are the frequencies that are present in the time domain signal? X of omega will let you know about that. So for example, I'm going to try to sketch something here. Let's say and I'm I'm going to see if I can sketch maybe a sinusoid with, so with this sketch, and this is time, and this is x of t, right? And I have in order to explain things, I've made it a little bit more dramatic than necessary, but I hope you are getting this information here. There are some high frequency elements to x of t that have a larger amplitude, and there are some low frequency, slowly changing aspects of x of t that have a smaller amplitude. So when you sketch x of omega, let us say I have absolute of x of omega, the magnitude of x of omega, because x of omega can be complex. So it will have magnitude and phase. Right now I'm only worried about the magnitude with respect to omega. This guy over here, yellow, that means that I have a larger amplitude at higher frequency. So that means that something like this. Higher frequencies, larger amplitude. Lower frequencies, lower amplitude. And if it is real, and even it will be having a symmetry, an even symmetry. But all those properties are coming later on. But if you see this, if this is 0 frequency, low frequencies are having lower amplitudes, higher frequencies are having higher amplitudes. That's what the kind of information you're getting from this, right? Questions, discussion about the first point. Frequencies present in time domain signal. Do you guys see how to view that? All right, now let's go for the second point here. The second point is knowing the frequencies is extremely useful in determining the sampling rate. At what rate I should sample x of t such that I can reconstruct it from its samples properly. I hope you see that if I sample this signal, I'm going to point out the samples, say black, right? So this is a continuous time signal, and I want to send it across to point B, right? From transmitter to receiver, I want to send it. And I want to send it using a digital device. Well, that means that I need to digitize it. At some point, I will have to make it analog so that I can transmit the radio frequency waves, say if you have a wireless channel. But at many times, it will be discretized. It will be a bunch of samples. So I store samples, I process samples. So if I want to sample x of t, which means I want to select certain values of x of t, which one should I choose? If I choose a very low sampling rate could result in this. I pick this guy, I pick this guy, I pick this guy, I pick this guy, right? Can I reconstruct the signal with this? You know what I'm going to get? I'm going to get this, like that. because I have this, and I have this, and I have this, and I have this. I will not get the signal that I sent clearly. So that is a consequence of choosing a low sampling rate. So I should have it higher. All right. How high? If I have it too high, if I have it extremely high, I may be able to reconstruct the signal. However, I will have to process a lot of samples. I have to store a lot of samples. Okay, so too low is bad, too high is bad. So of course there is a sweet spot, right? And the sweet spot, and we will prove this later on, is referred to as the Nyquist criteria. Nyquist criteria says that if you want to be able to reconstruct your sampled signal, then you need to sample x of t at least twice the maximum frequency of the signal x of t. So if I say, yeah, the maximum frequency, the highest frequency in x of t is f max. If I say this, then I need to sample x of t at least twice f max. In terms of a figure, let's take a look at this. If my x of omega went like that, right, and it became 0 here, that would be omega max, right? That's the highest frequency. And from omega max, I can get f max. How? I just divide it by 2 pi. And once I know f max, I can use Nyquist criteria to find the sampling rate that will allow me to reconstruct that signal. A lot more on this topic when we talk about sampling and communication systems. But what I want to really talk about now is that in order for us to sample the signal, I need to know its frequency content. Specifically, I need to know its highest frequency, for which I need x of omega to know what maximum frequency is, right? I need to know this. I can also use, okay, let me erase this now and let's go to the next point. The next point is frequency equalization. So I'm going to just talk about it for a minute. What is frequency equalization? Suppose that you have a communication channel between you and me. And it so happens that all the low frequencies in my voice are going to you okay. But when I talk in a very high frequency pitch, let us suppose that those get attenuated. Those frequencies are getting attenuated. And I would know this by knowing the Fourier transform of the channel between you and me. And once I know that, and if I observe that the high frequencies are getting attenuated, I can use that information to do some pre-compensation or post-compensation for the high frequency elements. In other words, I can amplify the frequencies that are getting attenuated once I know that Fourier transform. Once I know the how the channel is treating the frequencies differently, I can do a frequency equalization so that for the receiver, low and high frequencies, all frequencies are appearing the same. So frequency equalization is another application where Fourier transform is very, very critical. Next point, filtering specific frequency bands. Well, if you know the Fourier transform of a radio signal that you're trying to, suppose you have a FM radio, you're trying to tune your receiver to a particular channel. If you know the Fourier transform of signals that are coming to your receiver, then you can apply those filters at the respective frequency bands. So knowing the frequencies or the frequency domain information is very, very useful even in that application. And this list keeps going. So I just pointed out a few that that are more relevant to what I do. All right, questions about this slide? I know there was a lot to unpack here, but we will revisit Nyquist criteria and frequency equalization and filtering specific bands later in the course as well. All right. Now I need you guys to participate a little bit. Suppose you only know this. Suppose you only know the frequency domain. You only know the Fourier transform of the signal. If you want to know when does this happen, when does this frequency occur, can you answer that with x of omega? Can you answer that question? When does this frequency occur? Say that is 1 kilohertz, say for example, times 2 pi. In the signal, do you know when does that frequency occur? No. So, no. So here, based on, not unless you do an inverse. Yes, absolutely. So to answer the question about when, you would need to find the inverse Fourier transform of the signal. When does this frequency occur? Well, find the inverse Fourier transform, you get this. So then you can say, oh yeah, that particular frequency happens between times 0 and 5 seconds. That is the reason why we have inverse Fourier transform. So you have Fourier transform to go from time to frequency, and you can address all these applications. And you also need inverse Fourier transform to know when do those frequencies occur. All right, let's move on. This is your first Fourier transform that you are evaluating. And there is a reason why it is in this form, because it's a standard result and it is pretty simple to evaluate. And we will do this using the Fourier transform definition. So we are trying to find the Fourier transform of e to the minus at u of t, where a is a complex number whose real part is greater than 0. This is example 4.1 in the primary textbook, the Oppenheim textbook. So we are given x of t, right? That's our x of t. The time domain signal. And it looks something like this, right? E to the minus t u of t, otherwise it is 0. And for this particular signal, we are trying to find the Fourier transform. All right, so plug and play, right? So let's plug in e to the x of t in the Fourier transform definition. We are using the direct integration approach here. x of omega is negative infinity to infinity. X of t, we'll substitute this there, e to the minus j omega t dt. If we are trying to integrate out t, we will be left with omega. X of omega equals negative infinity to infinity, e to the minus at u of t from the signal, e to the minus j omega t dt from the definition. Because you have a u of t there, I only need to evaluate, because you have a u of t there, I only need to evaluate it from 0 to infinity. I do not have the signal, a non-zero thing less than 0, for time less than 0. And for those times, u of t is 1. So you have a 1 times, right? E to the negative at, e to the negative j omega t can be combined into one exponential. You integrate the signal, you substitute the limits, you will find that this comes out to be 1 divided by a plus j omega, where a is a complex number whose real part is greater than 0. In the sketch, I have assumed that a is real. Now, once you know this, you have got a Fourier transform pair. This is the first Fourier transform pair that we have come up with. E to the negative at u of t with real part of a greater than 0. The Fourier transform pair, and let me write that over here. Fourier transform pair is x of omega, which is 1 divided by a plus j omega. Is x of omega complex? Yes. If it is complex, then I need to find its magnitude. I cannot just say sketch x of omega, right? I can say sketch magnitude of x of omega, and I can say sketch phase of x of omega. I cannot just talk about x of omega. So if x of omega is complex, I need to evaluate its magnitude and phase spectra. Okay, what is spectra? It is plural of spectrum. So what is spectrum? Can I say it is the behavior with respect to frequency? The entire graph. Well, you have both of them, right? You have magnitude spectrum and phase spectrum. So magnitude spectrum is on the left, phase spectrum is on the right. So you have both of them. Jacob says spectrum is the worst internet provider. All right, that's funny. Well, spectrum is essentially indicating that my x-axis is omega or f, right? It's the behavior with respect to frequency. So how does magnitude of the function behave with respect to frequency? Well, for that, I would need to find the magnitude of x of omega. What is the magnitude of the function? Well, x of omega is 1 divided by a plus j omega. So what is the magnitude? X of omega is 1 divided by a plus j omega. The magnitude of x of omega would equal the magnitude of 1, which is 1, divided by a squared plus omega squared. How about phase? Phase of x of omega would equal phase of 1 minus phase of a plus j omega. Phase of 1, that is a real number, so that lies on the real axis, so that's 0 degrees, minus what is phase of a plus j omega? Well, tan inverse omega by a, right? Negative tan inverse omega by a. Well, so I'm a variable, right? A could be anything, but I'm trying to find the behavior with respect to omega. So you bring up a good point. How were you able to make the sketch? Well, for the sketch, I just assume that a is 1, right? I just assume that a is 1 to be able to sketch this out. I cannot find a. A is of a is, so x of t equals e to the minus at u of t. A needs to be given to me, right? So let us see what happens over here. When frequency is 0, what do you have? 1 divided by a. So that point essentially is 1 divided by a. But for the sake of this plot, I had to pick a value, an arbitrary value of a constant, and I picked 1. So let's see. What can we know from this plot? Does this signal e to the minus at u of t have a lot of high frequencies or a lot of low frequencies? Like where is the higher magnitudes? Low frequencies, absolutely. You see this? Low frequencies are a lot because it's e to the minus at u of t. And then as you go higher in terms of frequencies, the magnitude of those elements is lower and lower. Next, we move on to the phase. Phase is negative tan inverse omega divided by a. We know how to find the phase. We just did that. And again, I used a equals 1 to be able to plot it out. So when omega is 0, I got 0. And when omega is 1, I got negative pi over 4. When omega is negative 1, I got plus pi over 4 and so on, because I picked a as 1. So the y-axis over here is phase of x of omega in radians. X-axis again is frequency omega. So magnitude and phase combined, you have the overall spectrum of x of omega. But this is something that gets overlooked. The fact that x of omega is complex, and you will have to individually address magnitude and phase spectrum. There will be two entities to observe. All right. Now this is an interesting example in that we are going to start using some tricks to find the Fourier transform. So we are trying to find the Fourier transform of a sine function, sine, or let's see, this is x of t, sine function, also called as what? Signum function. So how do I find that out? Well, how does it look like? It looks like this. Sine is positive, sine is negative. So x of t is 1, for let's see, x of t is 1 when time is greater than 0, and x of t is minus 1 when time is less than 0, and at 0 there is a discontinuity. So that's the definition of the sine function or the signum function. That's our x of t now. Now this signal is not absolutely integrable, but so to find the Fourier transform of this, we will have to use some tricks to find the Fourier transform. And the trick is this. The trick is, consider a new function x prime of t with a tending to 0, which is defined as the sine function. So look at what we are doing here. This is what is x prime of t. X prime of t is defined as, let's see, e to the, in red you have e to the minus at. That is the one that is yellow here, for time greater than 0. And when time is less than 0, you have negative e to the plus at. Negative e to the plus at. You can actually write that as what? E to the minus at u of t plus e to the minus e to the at u of minus t. So we are trying to find the sine function, but we are trying to use an exponential here. And then once you evaluate the limit a tends to infinity, this decaying exponential will become a step there, and this exponential will become a step there as you evaluate a tending to 0. So the approximate Fourier transform is going to be x prime of omega. Again, we have to do this piecewise. So for the first piece, when time is less than 0, you get negative infinity to 0. There is a negative sign on the exponential, e to the plus at, and then the rest pieces are the definition of Fourier transform. The other one, time greater than 0. So the limits are 0 to infinity. The function is e to the minus at, and then the rest of them, the rest is the definition of the Fourier transform, the direct integration. Once you do the integration, substitute the limits, simplify, you get these two things. One is for the blue and the other is for the yellow. And now you evaluate a tends to infinity, a tends to 0. Now when you evaluate a tends to 0, you get your answer for the Fourier transform of the sine function as 2 divided by j omega. So the Fourier transform pair that we have next is for the sine function. The sine function, the Fourier transform is 2 divided by j omega, and the inverse Fourier transform of 2 divided by j omega is the sine function. Again, it is complex, it will have magnitude and phase. Now let us try to do this. I want to find the Fourier transform of a rectangle, and I'm defining this rectangle as a function. So the argument of this rectangle function is t1. So that's that and that. And the height of this rectangle is a scalar m. And I want to find out its Fourier transform. What do you think it should look like? What function should it be? The Fourier transform of a rectangle should be the Fourier transform of a rectangle should be. Uh, 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 uh. Remember what we did with the sinc? Yes. That's what we did, right? That's how we went from Fourier series to Fourier transform. We said we are trying to sketch it out. T tends to infinity. All the Fourier series became closer and closer to each other, and we got a sinc function. The envelope was a sinc. That was the continuous sinc that we evaluated for the rectangle. So I want you guys to have this paired up in your head. Rectangle, the Fourier transform pair is a sinc. Rectangle and sinc are Fourier transform pairs. So if you have a sinc in the time domain, its Fourier transform will be rectangle. If you have a sinc in the frequency domain, its inverse Fourier transform will be rectangle in the time domain. Rectangle and sinc are Fourier transform pairs. Let's try to evaluate this Fourier transform. Let's do it by direct integration. All right, so let's see. I will use red here. I will say x of omega is, I have m, which is a scalar, so it comes out of the integration. I don't need to do integration from negative infinity to infinity. I only need to do it from negative t1 to t1. Then I have e to the 1 times, well, why the right one? Is just e to the negative j omega t dt. That's it. So what do you have? You have m e to the negative j omega t divided by negative j omega. Substitute the limits t1 and negative t1. What do you get? You get negative 2 times m divided by omega multiplied by e to the negative j omega t1 divided by 2j minus e to the plus j omega t1 divided by 2j again. This will equal 2 times m divided by omega. Let's see, what is this guy? This guy is essentially negative sine omega t1 using Euler's. So negative sign cancels out with the next negative sign. You get 2m divided by omega sine omega t1. And if I want to express it in the form of sinc function, I need to do a sine x over x, right? So I want, if I have sine of omega t1, I want a omega t1 in the denominator as well. So what I'll do is I will multiply and divide by t1. So what do I get? 2m t1 sinc omega t1. That's the Fourier transform of the rectangle that we defined here. Questions about this example? All right, let's move forward. The Fourier transform of a rectangle is a sinc. Note that. You are going to see this many, many times. So have that, the details of the functions you can, you can figure out later, but those two words, sinc and rectangle, should appear in the form of pairs in your head. X of t, if it is a rectangle, that means that it is 1 between negative t1 and t1, it is 0 otherwise. X of omega is 2t1 sinc omega t1. We just derived it for the general case earlier where we had the m. In this case, m is 1. We get this particular transform pair. On the left side, we have a rectangle in time domain. On the right side, we have x of omega, 2t1 sinc omega t1, where t1 is this. Now, note this. The area under x of t is 2t1. Is that right? This area. Where do you see this 2t1 again? Right there. I'm trying to emphasize this so that I can show you a very interesting result on the next slide. In front of the sinc, yes. Now, just to recap, the definition of sinc is sine x over x, and it looks like this, and it has, at x is 0, you get a 1, and when x is pi and 2 pi and 3 pi and so on, or negative pi, negative 2 pi, negative 3 pi and so on, all those are the zero crossings of the sinc. That's the definition of sinc function. Now the interesting result is this. Area under the time domain signal x of t is cap x of 0. What is cap x of 0? The value of the signal x in frequency domain at omega equals 0. So that's like the DC term. The DC term, the value is the area under the time domain signal. And we can quickly prove this. Just substitute omega equals 0 in our definition of Fourier transform. What do you get? X of 0 equals negative infinity to infinity, x of t, that's it, dt. So area under x of t is value in the frequency domain at omega equals 0. In other words, I can do this. Time x of t negative 2, 3, 1, 0. Fourier transform pair magnitude of x of omega, omega 0. What is the value here? What is the value on this? Alan says 2.5. So I don't know how it does at frequencies apart from that. And I also don't know, what is the Fourier transform of a triangle. I have not done it for a sawtooth waveform yet. But by using this simple property, I right away know what is the DC value in this. Right? So that 2.5 is that's the value of x of omega at omega equals 0. Adrian says, does this mean that for the Fourier transform, the zero term is always non-zero for non-periodic signals? Ah, yes, it is the same explanation as we found for a sub 0, but now those Fourier series coefficients are multiplied by t, right? So it's a sub 0 times t. That's what we that is the sampled version of x of omega. So, but they are related, and you're right. It is sort of the same idea there. Does this mean the Fourier transform? So Adrian, I don't understand the zero term. I didn't quite get what you mean by the zero term. At omega equals zero, non-zero. Oh, no, no, no. You can have this, right? So the area might cancel out. It's not necessarily zero. It might cancel out. All right, let's move on here. Also, if you look at it in the other angle, which is the inverse Fourier transform, the area under the frequency domain signal will be the value of the signal in time domain at time 0 divided by 2 pi. You have to remember the 2 pi here. This is again from the definition, right? X of t equals 1 over 2 pi integration negative infinity to infinity x of omega e to the j omega t d omega. You plug in t equals 0. What do you get? X of 0 hold on. Area, oh, this is 2 pi times. Right, x of 0 times 2 pi, that equals integration negative infinity to infinity x of omega d omega. So you can find the area of the curve in time domain. That will give you the value at 0 in the other domain, and you can do it similarly for area under the frequency domain will give you the value of the signal at t equals 0 times 2 pi. All right, let us move on to some transforms involving delta functions. What is the Fourier transform of an impulse? Delta of t. Apply the definition. When you apply the definition, what are you doing? Integration negative infinity to infinity delta of t e to the minus j omega t dt. The impulse is valid only when t is 0. Evaluate e to the negative j omega t at t equals 0. What do you get? E to the negative 0. That's 1. You are integrating for all time. That means you are integrating over the impulse. That means you will get an area of 1. So that's just the properties of an impulse function that we saw earlier in the course. So the Fourier transform of an impulse is 1. What is the implication of this? The implication is the impulse function at time t equals 0 corresponds to a constant in frequency domain. So in time, it was that. In frequency or omega, it was that. You guys remember when we were talking about convolution and the response of LTI systems, and we said, hey, so what's so nice about an impulse function? And I said, yeah, it has all frequencies. That's exactly what I meant. The impulse function has all frequencies. It treats all frequencies the same. Yes. Now, what is the inverse Fourier transform of delta of omega? What if you have an impulse in the frequency domain? Well, if you have an impulse in the frequency domain, then the inverse Fourier transform of delta of omega by using the definition of inverse Fourier transform is going to equal 1 over 2 pi integration negative infinity to infinity delta of omega e to the plus j omega t d omega. And again, because it's an impulse at omega equals 0, you evaluate e to the plus j omega t at omega equals 0, you get a 1 there. You are integrating over that impulse, so that will contribute to a 1. 1 over 2 pi remains as is in the result. In other words, that 2 pi, instead of saying 1 divided by 2 pi, the Fourier transform pair is just delta omega. If you bring that 2 pi up over there, you get the Fourier transform pair of 1, and the Fourier transform of 1 is 2 pi delta of omega, which means in time domain, if you have 1, then in frequency domain, you will have an impulse weighted by 2 pi. So what is the next pair of words that we need to associate? Like rectangle, sinc. The next pair is impulse and a constant. The Fourier transform of an impulse is a constant. The Fourier transform of a constant is an impulse. What frequencies does this have? No frequencies, it is just DC, right? At zero frequency. The implication of this, the impulse function at omega equals 0 means that the signal contains one frequency, which is the zero frequency or the DC term. All right, let us go on to the Fourier transform of a unit step. The Fourier transform of a unit step x of t, I can write x of t as the summation of half sine function plus half constant. I already know the Fourier transform of half sine function from earlier. I also know the Fourier transform of 1. So I am kind of, doing something unfair here. What is that? I'm using linearity property here of Fourier transform that I have not yet proved and talked about. I will do that later on, but that's what I'm using right now. I'm using the linearity property of Fourier transform. Similar to how we had earlier with linearity in Fourier series, there will be a linearity property for Fourier transform as well. So if I can express x of t as the sum of two signals x1 and x2, this guy is x1, this guy is x2, which is half sine t and half times 1, its Fourier transform will be half 2 divided by j omega, that was the Fourier transform of the sine function, plus half times 2 pi delta of omega, that is the Fourier transform of 1 from before. Simplify this, you get the Fourier transform of the unit step, which is 1 divided by j omega plus pi times delta of omega. In the bracket notation, we can write that as Fourier transform of unit step is going to equal 1 divided by j omega when omega not equal to 0, and it is going to equal pi delta omega when omega equals 0. The next one is a linearity property. We have a and b as scalars. You have seen linearity property play out in convolution, Fourier series. So this should be a little bit straightforward now. the linearity property for Fourier transform says that if you have two signals x1 and x2, for which you have their Fourier transforms as x1, oh, let's do this way. You are given this x1 of t, the Fourier transform is x1 of omega, and x2 of t, you are given the Fourier transform as x2 of omega. So given that, then a scalar a times x1 of t plus b x2 of t, the Fourier transform of that, the Fourier pair of that, will be a multiplied by the Fourier transform of x1 plus b multiplied by the Fourier transform of x2. And you can prove this by considering a new signal x3 of t, which is the scaled and summed version of a x1 of t plus b x2 of t. Then the Fourier transform of x3 of t can be written by using the direct integration of Fourier transform as integration negative infinity to infinity x3 of t, which is that, which is ax1 plus bx2 e to the negative j omega t dt. And because a and b are scalars, they come out of the integration. You will be left with x1 and x2 inside. And if we now notice them in separate integrals, you can see that they are essentially the Fourier transform of individual x1 and x2 of t. So this is a quick proof that linearity applies for Fourier transform operation. We will go on to see that it is along with the standard Fourier transform pairs, this is a very useful property. So just to have a little recap now, the Fourier transform pair, rectangle and sinc. The Fourier transform pair, constant and an impulse. The Fourier transform of the sine function and the Fourier transform of the unit step. And we looked at one property, the linearity property of Fourier transform. All right, so I'm going to stop the recording here, and then we can take some questions on the homework.